Good morning. I'm Tammy, and I'm in electrical engineering, and I'm going to be a senior.
I'm Scott Tripp. I'll also be a senior, but in aerospace engineering. We're going to talk about the Nanosatellite pipeline power system.
And we are working for SPFL and RACS, working under Professor Gilchrist and Professor Cutler.
First question is, what is the Nanosatellite pipeline? And that is a concept that was developed by one of the recent grad classes in aerospace engineering to produce high-volume research for nanosatellites here. We want to have yearly mission proposals and development cycles. We want to have a very high volume of research turnover on this. We also want to be able to streamline the development process, reuse systems from previous missions, adapt old systems to new requirements, and another key important factor is having the experienced students who've already had a mission or two help the newer students come up to speed faster. The whole idea is to increase the efficiency so that we don't have to waste time re-engineering systems that have already been solved. What's our part? We're working on the electrical power system. Critical component to all satellite missions is power. If you don't have power, you don't hear from your spacecraft. You don't know if anything's happening. Unfortunately, power systems are also have one of the highest failure rates of any satellite system. Most spacecraft that have failed are due to power. Professor Cutler has had a few recent missions. Well, even though they worked at first, they eventually suffered problems with their power system before they died. Another recent mission that was launched, never heard from, but most people suspect that it was probably the power system that failed. To complicate things, we have to work on a very rapid development schedule. RACS needs to be delivered this fall, even though it only started 1 year ago when the National Science Foundation asked Professor Cutler to build this satellite for them to explore space weather. M-Cubed has been under development for a little longer, but we're hoping to get it launched in the near future as well, probably delivering sometime this winter if all goes well. So both missions are on a very tight timeline right now.
Here's a block diagram of our overall system. On the left, you can see the solar arrays. This is where we get our energy from the sun and we convert it into power. With the LT3685, these are our DC-DC converters, and we convert the voltages into the necessary voltage needed for the battery, which is here. Our PTH08080 is our output bus regulator, and we convert the power from the battery for the loads into the necessary voltages, which is either 5.0 or 3.3.
Solar input for the spacecraft. Most spacecraft today are powered on solar energy. There are alternative energy sources such as nuclear, long-duration batteries, and so on. But solar cells are nice because they have a much longer lifespan, and satellites on orbit aren't generally constricted to the size of their solar arrays, unlike here on Earth. However, we have a different reason for using solar arrays, and that is we're very size limited, so we can't fit much else in there. But we also can't fit many solar arrays, so we need to be very careful with how we use our solar input. We need DC-DC converters on the inputs for very high efficiency. We also need to be flexible because this power system won't be used for just RACS or just M-Cubed. It'll be the core of power systems used for future missions as well, possibly even for missions outside this university. So we need to be able to be very flexible with the solar input. We have DC-DC converters on the input so that we can convert whatever voltage comes off the solar arrays into a usable voltage for charging the battery and running system loads. One issue that comes with using solar power is an effect called latch-up. And that's when you take more current out of the solar cells than they can handle, and all of a sudden you lose all the power that you had. Just a little bit more and you lose everything. And the only way to get out of it is to reset all of your loads back down to nothing and start over. Fortunately, you can't afford that in a space mission, so we need a way to get around that. We develop comparator circuits that will actually sense where the voltage and currents coming out of the solar arrays are, and will tell the converter to stop trying to draw more power if they ever try to draw more power than the solar arrays can handle. Unfortunately, these comparators are very finicky and difficult to tune, so it takes a lot of development to make them work. We selected the lithium-ion batteries because they're very high energy density, which means for the weight that you get, you can store a lot of electricity in them. They're also very durable, they're difficult to break, they're easy to recharge, and most importantly, they have heritage in space. We don't want to send components into space that have not flown before if we can at all help it. It only increases the risk when you do that. And you can charge them very easily simply with the available current off the solar arrays, so it eliminates the complexity of needing a standalone charging unit.
Each satellites have loads that need specific voltages, and so for ours is 5.0 and 3.3 volts, and we also need a raw battery voltage. Our DC-DC converters regulate the output voltage, and they have fairly high efficiency, roughly around 85 to 95%. However, they do produce noise, and we use filters to reduce the voltage ripples. Many other systems cannot tolerate high voltage ripples.
Okay, that basically covers our electrical power system. Just want to say that anybody who's interested in going into projects should definitely pursue it. SURE is a great way to get funding for the summer research. Provides many great experiences in both learning about your own systems as well as others. But there are other opportunities as well. The big things I want to say is find a project that piques your interest and get involved. You learn a lot more than you can in the classroom.
I agree. This is actually the first time I'm doing research, and research is a very good opportunity to apply your knowledge in class into actually doing something hands-on. And I'm actually planning to work on the satellite over the fall semester also.
That's about it. Thank you for watching.